What is powdered iron core inductor and how does it function? A powdered iron core inductor is an inductor that uses a core made from powdered iron particles bound together by a resin. These cores have specific magnetic properties that make them useful in various electrical and electronic applications, especially in power conversion, filtering, and energy storage. The structure of a powdered iron core inductor consists of two primary components, the core and the coil. Below is a detailed breakdown of these components. 1. Powdered iron core. Material. The core is made from tiny particles of iron, which are insulated from each other with a non-conductive material, often a resin binder. This insulation helps reduce eddy currents that can cause energy loss within the core. Shape. The powdered iron core can come in various shapes, such as toroidal, donut-shaped, cylindrical, or E-shaped, depending on the specific application. Magnetic properties. The powdered iron core has a relatively low permeability compared to other core materials like ferrites, but it offers a higher saturation point. This makes it suitable for handling higher current levels without saturating the core. 2. Coil, winding. Conductor. The coil is typically made from copper wire due to its excellent conductivity. The wire is wound around the core to create the inductor. Turns. The number of turns of the wire around the core determines the inductance value. More turns generally result in higher inductance. Insulation. The wire is often insulated with a thin layer of enamel to prevent short circuits between turns of the coil. Winding method. The coil can be wound in various configurations, such as single-layer, multi-layer, or distributed winding, depending on the desired electrical characteristics. 3. Core coating, optional. The powdered iron core may also be coated with an insulating material or resin to provide mechanical protection and additional electrical insulation, ensuring that the core does not come into direct contact with other circuit components. 4. Terminals, leads. The ends of the wire coil are connected to terminals or leads, which provide electrical connections to the rest of the circuit. Visual representation. Core, at the center, made of bonded powdered iron particles. Coil, wire wound around the core to form an inductive element. Leads, extensions of the wire coil that connect the inductor to an external circuit. This simple yet effective structure allows powdered iron core inductors to perform their function in electronic circuits by providing inductance, energy storage, and filtering capabilities. A powdered iron core inductor functions by storing and releasing energy in the form of a magnetic field. Here's a detailed explanation of how it works. 1. Magnetic field creation. When an electric current passes through the inductor's coil, a magnetic field is generated around the coil, in accordance with Ampere's law. The powdered iron core enhances this magnetic field because iron has better magnetic properties than air or other non-magnetic materials. The magnetic field strength depends on the number of turns of the wire, the current flowing through the wire, and the magnetic permeability of the core material. 2. Energy storage. The inductor stores energy in the magnetic field when current flows through the coil. The amount of energy stored is proportional to the square of the current and the inductance of the coil. E equals 1/2 Li superscript 2, where E is energy, L is inductance, and I is current. Unlike a capacitor, which stores energy in an electric field, an inductor stores energy in a magnetic field. 3. Inductance and opposition to current changes. Inductors resist changes in current. When there is a sudden increase or decrease in current, the inductor generates a voltage that opposes this change, according to Lenz's law. This is why inductors are often used in circuits to smooth out current fluctuations. For example, in a DC circuit, when the current is initially turned on, the inductor resists the rapid increase in current by generating an opposing voltage. Once the current stabilizes, the inductor allows the current to pass through with minimal resistance. When the current is turned off, the inductor tries to maintain the current flow by releasing the stored energy in the magnetic field. 4. Frequency response. Inductors have frequency-dependent behavior. At low frequencies, the reactance, opposition to current, of an inductor is relatively low, allowing current to pass through more easily. At higher frequencies, the reactance increases, which means the inductor impedes the current more. This makes powdered iron core inductors useful for filtering out high-frequency noise in power supply circuits. The powdered iron core helps to control the frequency response of the inductor, offering stable performance across a wide range of frequencies. 5. Reducing core losses. One of the significant advantages of using a powdered iron core is the reduction of core losses. In a solid iron core, large eddy currents, circulating currents within the core, can form due to the changing magnetic field, leading to energy loss in the form of heat. The powdered iron core, with its insulated iron particles, reduces these eddy currents. The small, discrete particles disrupt the paths for eddy currents, minimizing the associated losses and improving efficiency, especially at higher frequencies. 6. Handling high currents. Powdered iron cores have a higher saturation point compared to other core materials like ferrite. Saturation occurs when the core material can no longer increase its magnetic field strength in response to an increase in current. Once saturated, the inductance drops sharply. Because powdered iron cores have a higher saturation point, they can handle higher currents without significant loss of inductance. Application of functionality. Energy storage. In power supply circuits, powdered iron core inductors store energy during one phase of the power cycle and release it during another, helping to smooth out the power delivered to the load. Filtering. In AC circuits, such as those used for signal processing or radio frequencies, inductors are used in filters to allow or block specific frequencies, depending on the circuit design. Noise suppression. In power lines and electronic circuits, powdered iron core inductors are used to suppress high-frequency noise. In summary, powdered iron core inductors function by generating a magnetic field when current flows through them, storing energy in that field, and resisting changes in current, all while maintaining efficiency through reduced core losses and the ability to handle higher currents without saturating. Powdered iron core inductors offer several advantages that make them suitable for various applications, especially in power electronics, filtering, and RF circuits. Here are some key benefits. 1. High saturation point. Handling high currents. Powdered iron cores can withstand higher magnetic field intensities before reaching saturation compared to other core materials like ferrites. This makes them ideal for applications where high current levels are involved, such as power supplies and transformers. 2. Cost effectiveness. Low material cost. Powdered iron is generally less expensive than other core materials like ferrites or specialized alloys. This cost advantage makes powdered iron core inductors a good choice for mass-produced, cost-sensitive applications. Widely available. The material and manufacturing processes for powdered iron cores are well established, making these inductors widely available at a lower cost. 3. Stable performance across frequencies. Broad frequency range. Powdered iron cores exhibit relatively stable magnetic permeability across a wide range of frequencies. This allows them to perform well in applications that require consistent behavior at varying frequencies, such as in RF circuits or signal processing. Controlled permeability. The permeability of the core can be adjusted by controlling the size and distribution of the iron particles, offering flexibility in design. 4. Reduced core losses. Lower eddy currents. The powdered structure of the core, with individual iron particles insulated from each other, helps reduce eddy currents, which can cause energy losses in the form of heat. This makes powdered iron core inductors more efficient, especially in AC applications where the magnetic field is constantly changing. Lower hysteresis losses. Powdered iron cores typically exhibit lower hysteresis losses compared to solid iron cores, contributing to better energy efficiency. 5. Thermal stability. Stable performance at high temperatures. Powdered iron cores generally have good thermal stability, maintaining their inductive properties over a wide range of temperatures. This makes them suitable for applications that involve high operating temperatures or fluctuating temperature conditions. Resilience to overheating. Due to reduced core losses, these inductors are less prone to overheating, enhancing reliability in demanding applications. 6. Mechanical strength. Robust and durable. Powdered iron cores are mechanically strong and durable, making them resistant to cracking or breaking under mechanical stress. This robustness is advantageous in applications where the inductor may experience physical stress or vibration. 7. Lower magnetic noise. Distributed magnetic field. Powdered iron cores create a more distributed magnetic field compared to solid cores, which can help reduce magnetic noise, EMI, in sensitive applications. This makes them useful in noise-sensitive environments, such as in communication equipment or precision electronics. 8. Versatile design options. Customizable properties. The properties of powdered iron cores can be tailored during the manufacturing process by adjusting the particle size, bonding material, and compaction method. This allows designers to optimize the inductor for specific applications, balancing factors like inductance, saturation current, and loss characteristics. Variety of shapes and sizes. Powdered iron cores can be manufactured in a wide variety of shapes and sizes, such as toroids, rods, and E-cores, allowing flexibility in design and application. 9. Lower harmonic distortion. Reduced distortion in AC applications. Powdered iron cores are known for producing lower harmonic distortion in AC signals, which is important in applications like audio processing, RF circuits, and power conditioning. 10. Suitable for power supply applications. Smoothing and filtering. In switch-mode power supplies, SMPS, powdered iron core inductors are often used to store energy and smooth output voltages, filtering out unwanted noise and ripple from the output, thereby enhancing the performance and efficiency of the power supply. In summary, powdered iron core inductors offer a combination of cost-effectiveness, high current handling, stability across a wide frequency range, and reduced energy losses, making them a versatile and reliable choice for various electronic and electrical applications. Powdered iron core inductors are widely used across various industries due to their unique characteristics. Here are some of the common applications. 1. Switch-mode power supplies, SMPS. Energy storage. In SMPS circuits, powdered iron core inductors are used in the energy storage phase, where they store and release energy during switching cycles. This helps regulate output voltage and current, making the power supply more efficient. Filtering and smoothing. These inductors are also used to filter out high-frequency noise and smooth the DC output in SMPS, reducing ripple and ensuring stable voltage delivery to the load. This is a converter. Boost, buck, and buck-boost converters. Powdered iron core inductors play a critical role in DC-DC converters by storing energy when the switch is closed and releasing it when the switch is open. This helps step up or step down the voltage as needed in power electronics, making them essential components in portable devices, automotive systems, and renewable energy systems. 3. RF circuits. Tuning and matching networks. In radio frequency RF circuits, powdered iron core inductors are used in tuning circuits and impedance matching networks. They help achieve the desired frequency response and improve signal transmission efficiency in applications like radios, communication equipment, and antennas. Oscillators. These inductors are used in LC, inductor capacitor, oscillator circuits to generate stable frequencies for RF transmitters and receivers. 4. Audio equipment. Crossover networks. In speaker systems, powdered iron core inductors are used in crossover networks to separate audio signals into different frequency bands, e.g., bass, mid-range, and treble, and send them to the appropriate speakers. Noise filtering. They are also used in audio amplifiers and other equipment to filter out high-frequency noise and ensure clean audio signal delivery. 5. Filters. Low-pass and high-pass filters. Powdered iron core inductors are commonly used in filter circuits to block or pass specific frequency ranges. Low-pass filters, for instance, allow low-frequency signals to pass while blocking high-frequency noise. EMI/RFI filtering. These inductors are often employed in electromagnetic interference, EMI, and radio frequency interference, RFI, filters to suppress unwanted noise and prevent it from affecting sensitive electronics. 6. Power factor correction, PFC circuits. Improving power efficiency. In power factor correction circuits, powdered iron core inductors are used to improve the efficiency of AC power systems by correcting the phase difference between voltage and current. This application is common in industrial equipment, lighting systems, and high-power electrical devices. 7. Transformers. Small transformers. Powdered iron cores are sometimes used in small transformers for isolation and voltage step-up/step-down applications. They are particularly useful in situations where size and efficiency are important, such as in small power adapters and chargers. 8. Inductive charging. Wireless power transfer. In inductive charging systems, powdered iron core inductors are used in the transmitter and receiver coils. These systems are commonly found in wireless charging pads for smartphones, electric toothbrushes, and other portable devices. 9. Automotive applications. Power electronics. In vehicles, powdered iron core inductors are used in various power electronics applications, such as DC-DC converters, power supplies, and motor control circuits for electric vehicles, EVs, and hybrid electric vehicles, HEVs. EMI suppression. They are also used in automotive EMI suppression filters to protect sensitive electronics from interference generated by high-power circuits, such as the ignition system or electric motor drives. 10. Lighting systems. LED drivers. Powdered iron core inductors are used in LED driver circuits to regulate the current supplied to the LEDs, ensuring consistent brightness and efficiency. They help improve the performance of LED lighting systems, making them more reliable and energy efficient. Ballast for fluorescent lamps. In fluorescent lighting, inductors are used in electronic ballast to limit the current flowing through the lamp, helping to start and maintain the light efficiently. 11. Renewable energy systems. Solar inverters. In solar power systems, powdered iron core inductors are used in inverters to convert DC power generated by solar panels into AC power for use in homes and businesses. Wind turbines. These inductors are also employed in wind turbine power converters, helping to manage the electrical energy produced and improve system stability. 12. Medical devices. Imaging and diagnostics equipment. In medical devices such as MRI machines and diagnostic imaging equipment, powdered iron core inductors are used in power supplies and filtering circuits to ensure stable and noise-free operation. Wearable devices. They are also used in wearable medical devices, where compact and efficient power management is crucial for reliable operation. In summary, powdered iron core inductors are versatile components that are used in various applications, ranging from power electronics and RF circuits to automotive systems and renewable energy systems. Their ability to handle high currents, reduce noise, and maintain stability across a broad range of frequencies makes them essential in many modern technologies. In summary, powdered iron core inductors are versatile components in electronics, offering a balance of performance, cost, and stability for various inductive applications.